Yeah, welcome back. And a lot of topics about the AI and about the hyperscale data center networks. Let's see some different. Yeah, welcome to this session. My name is Shuai. I'm from Alibaba Infra Services team. I'm the software engineer responsible for the SONiC development. And with me, I have Jason Boss from Cisco. He is the principal software engineer of Silicon One team. In this presentation, I will talk about our experience that building our Predictable-WAN using the SRv6 and SONiC-based white box. This is a very high-level diagram about Alibaba Predictable Network Framework. You may see this page in the previous session. Our vision is to build an end-to-end predictable network based on Ethernet, including several important parts. On the left bottom, it's our hyperscale data center network. We build the very high bandwidth and high radius Ethernet switches and optimize it for AI and machine learning workload. On the right bottom is our edge network. We build our own programmable smart network plans, which including service switch and our second generation smart switch with DPU. On the top, we have the global network, including our elastic service router and elastic peering fabric. In this presentation, I will focus on our global network. To simplify the global network, we utilize single product stack, IPv6, and SRv6, and single chip white box. Actually, we build all our white box using the single chip. We love single chip. And of course, we use the SONiC for all our devices. With SRv6 programmability, we can provide predictable network service to every single user and application in the global network. This is part of our global network, our use case, which is our global network is used to connect different regions for huge east to west traffic. It has two major roles. One is the elastic service routers as PE router, and the elastic core as the P router. In our first phase, we deployed our SONiC-based router as ESR. The ESR device is the SRv6 headend, which supports SRv6 VPN feature. And in the middle, it's the commercial router as the P node. On the ESR router, for a single tenant, we allocated 4 different WAFs. The root WAF is used to receive the routes from the CE device. The other 3 WAFs represent different service quality for this tenant. For each of them, we allocated different DD46 VPN seed. When the root WAF received a route from the CE, it will redistribute to other 3 WAFs, then advertise them to remote ESR devices. Then all the 3 WAFs will have exact same routes from the user, but has different VPN seed to represent different service quality. For the user, they can choose 2 different ways to choose different service quality. The first option, they can use the DSCP. Then on the ESR device, we used the ACL PBR rule to match the DSCP, then steering the traffic into one of the 3 WAFs. Since the route in the the second option is that they can use the UNI DT46 service seed. Then on the ESR device, it will decap the UNI SRv6 seed and steering the traffic into one of the 3 WAFs. Since the route in the 3 WAFs has VPN seed, The traffic going out from the ESR device will has different VPN seed encapsulated, which can be used to represent different service quality. Then the EC device will do another SRMPS-based traffic engineering. This is the whole idea for us. For the total solution, we call it as hierarchical traffic engineering. Of course, in our next phase, we will enable the SRv6 policy on the ESR device on the PE router to implement the end-to-end SRv6 traffic engineering. Then the P device, the P router will be more simple, and we can remove the MPLS feature. This is another use case for our peering network, which carried the south-north traffic. We used the SONiC-based white box to replace commercial router to peering with the service provider. We used the pizza box to build a small class, which including the span and leaf devices. Between the span and the leaf, it's the SRv6 fabric, which used the SRv6 TE to steering the traffic from the span to leaf to the service provider. In this system, we also has local controller which is running the BGP to peering with the service provider. The local controller also used the BGP to advertise the routes into our span and leaf nodes. To support the above two scenarios, we developed our own hardware, used the routing silicon for our routing platform. For the SONiC, we developed the SRv6 VPN and the traffic engineering feature. For this routing platform, it also supports large-scale routes. In our case, 2 million routes needed to support. And it can support the BFD, SBFD, BFD echo for monitoring SR policies. As you know, initially SONiC is designed for hyperscale data center switches, not for the router purposely. We met lots of problems for our router scenarios, like routing install performance, routing convergence performance, the communication channel between the FR and the SONiC. But SONiC gave us a very good starting point to build our nodes for the router. We initiated the SONiC sub-working group for the routing with Microsoft, Broadcom, Cisco to solve these problems with the community. And we have been working with our silicon vendor, Cisco, to extend the SONiC to support SRv6, especially on the site header definition and implementation. Now, Jason from Cisco will talk about SRv6 technology and their work on the site.
Thank you. So I'll just go through really briefly some of the technologies that we added to SI and are in various stages of being upstreamed into SONiC in order to enable this. So just a quick brief overview, like why use SRv6. One main reason is that it allows you to do basically source routing and traffic engineering over an existing IPv6 network. The only devices, unlike say MPLS, that need to know about the fact that you're doing this routing are the ones that are actually SRv6 aware, and the other ones in the middle are just doing basic longest prefix match, ECMP standard types of things. But SRv6 can also do more, and particular here, we're extending also to support VPN. So if we look at like a VPN scenario here, basically what's happening in this very, very simple topology, I'll show a picture of a more complex topology in a couple slides, but in this very, very simple topology, you can simply route to this :200 device on the TOR-B on the right side, simply through standard longest prefix, best effort reachability. This is not doing any segment routing at this point. or any traffic engineering, and simply encode the fact that you want VRF 145 in the LSBs of the IPv6 address. And that device will recognize it, realize that it's part of this VPN, and then be able to route it within a specific VRF that's on that right side there. So that allows you to do a very simple VPN service where the blue part of that prefix there, the DIP, gets you to that device, and then the yellow part is understood just by that device as being that VPN. This could also be extended to traffic engineering. So if you're combining the VPN with the traffic engineering, here I'm showing you with UCID encoding. There's a couple different ways of encoding SRv6. You stack a whole bunch of IPv6 addresses together with segment router headers. This fits better on the slide. It's also what's being deployed here. And it's basically, you stack together the different nodes. Here I just put them as L4, S1, L6, the 3 different nodes you want to take. And basically each node that's SRv6 along the way will pop that out and left shift everything else 16 bits. Pop it out, left shift at 16 bits. And basically the source can steer those packets through the network on a traffic engineered path. So that's basically how you can combine that, and at the end it'll understand that it's a VPN and do it. The key thing is at every point here, that's a fully routable IPv6 address. So if there's some intermediate nodes that exist that don't know about SRv6, they just do best effort routing to the next node indicated by the next SID or segment identifier. So if we look at what was already in SCI, SCI already had support for the SID entry. Of course, implementation had to be done, but SCI also already had support for the SID entries that indicate the VPN SID, the decap and lookup in a VRF behavior that can be programmed for the destination endpoint, and also the ability to specify the VRF. And head-end behavior had some support, but it previously specified everything collapsed down into one IPv6 next hop. So this is actually a picture from the SCI spec itself. So I just took that from there, so that's why a little low res. But the key there is that you would resolve your routing table here, or if an ACL, if you're doing like some sort of policy-based routing, down through ECMP, and you end up with just a single SID list, which would contain both your traffic engineering path and your VPN, if you were doing VPN. So you could do it that way. It would work, but it has a problem. Because when you look at a more complex topology, you have a mix of an overlay and an underlay that exist. There's some overlay network that has some VPNs, some service IDs that are being propagated, and then a shared underlay network that actually has all your traffic engineering paths. And this fact means that you have a combinatorial problem on the previous slide here, where you have to basically create each of your next hops for every combination of segment routed tunnel times every combination of VPN that you're doing over that. So that becomes a bit of a problem there that needed to be solved. And not only with that, you would have to also replicate your ECMP groups, and that could cause problems with convergence, scale, and things like that. So basically what was done was to decouple this. One mode of decoupling that was done was in order to allow these VPN SIDs to be programmed per input VRF. So this is something that would be very common if you're familiar with VXLAN. You have a tunnel map, and it says, hey, for every input VRF, here's the VPN SID to use for a given endpoint. And then another method that was used was to allow also the ability to, for a given IP prefix that's being routed, specify what the VPN SID is. And this is all done in a tunnel map, so it's per endpoint that you're trying to reach. So this allows for more flexibility where that VRF information isn't based on your, or that VPN SID isn't based on your local VRF, it's based on some signaling of a remote VRF that you're trying to reach. And you want something more flexible than just using something like a local VNI. This is for folks at home, you can pause the video and take a look at this, but this is kind of the full object model for SCI here. Additional capabilities that we added here in order to support this was also the support for SBFD and SRv6 NCAP for BFD. Because one of the key factors when you're segment routing or traffic engineering through tunnels across a network is you want to be able to switch over from one tunnel to another. And you want to be able to monitor that specific path, that specific tunnel path. And by doing this, you can just add a SRv6 or encapsulation type to BFD and specify the full SID list that provides the path to the destination you're trying to reach. We also chose SBFD as the primary method here. Of course, you can do it with traditional BFD, but SBFD has some advantages. The primary advantage of SBFD is that only one side really needs to know the state of every single session that's there. One side is configured as basically a dumb reflector, and any SBFD packets or sessions that come in, it's going to just send the packets back And that allows for whichever side knows about the tunnels that are trying to be monitored to send it. Of course, you can also have the other side be an initiator for its sessions and monitor reverse tunnels, but it avoids that negotiation problem where every side needs to kind of agree on a bunch of parameters around speed to send packets, the current state, and have kind of a more complex negotiation protocol. For these kind of tunnel situations, the SPFD protocol works a little bit better. And so that's, we added that to the SI headers there and did some implementation for it. The other technology that's a bit more of a recent addition is the SRv6 path tracing, which basically provides a telemetry type of functionality. So you can take a packet, if it's an SRv6 path tracing packet, every device that's path tracing capable and configured and enabled along the way will encode some information in the path tracing header. It's a very compact, just a few bytes of information, but it provides the record of the packet path, basically the timestamp at every node, so you can identify congestion if there's delay that's happening. You can put load information into that stamping of the packet as it traverses every single node of the network, so you can see if I'm sending packets to the network, what path are they actually taking, and get that telemetry from that. So this one was more recently added to SI, and there's some work to upstream that in SONiC as well. So just going to the call to action, I think the SONiC routing group, working group was talked about yesterday by Eddie from Alibaba. Just would like to mention again here. So all the work to get this introduced into SONiC, as well as additional enhancements to improve the behavior of SONiC, the overlay, underlay separation, prefix independence convergence, the BGP pick, everything related to that is being done now through SONiC working group, and it's an open thing. I think there's a meeting also even tomorrow to do some reviews with that. In addition, the upcoming SRv6 SONiC features, Alibaba's working on the upstreaming of the VPN. The path tracing is in SI now, so that pull request is done, and there's some, it's on the roadmap now to also upstream that into the SONiC side, or to add that to SONiC.
Thank you very much. Any questions? Any questions from the audience? All right, thank you.